Deep at the center of the Milky Way sits Sagittarius A star, a supermassive black hole. Because it rests exactly at the galactic core, we naturally assume it acts as the ultimate gravitational anchor, the heavy center point keeping our entire galaxy from flying apart. This animated diagram compares the mass of that central black hole against our galaxy. In our solar system, the Sun holds 99.8% of the mass, dictating the orbits of everything around it. But Sagittarius A star contains just 0.001% of the Milky Way's total mass. Mathematically, a central object that small cannot exert enough gravitational force to control the outer arms of a galaxy. This massive discrepancy is the origin of the missing gravity problem, the search for the elusive, invisible substance known as dark matter. To understand what is happening, we have to look at the strict physical laws governing how objects grow. If a planet accumulates too much matter, roughly 10 times the mass of Jupiter, its own gravity squeezes the core so intensely that it ignites into a star. Stars have a strict cap as well, known as the Eddington limit. If a star grows beyond 250 to 300 solar masses, the intense outward radiation overpowers the inward pull of gravity, causing the star to blow itself apart or collapse completely. Black holes are the single exception to these physical laws. They are the only objects in the universe completely exempt from any natural growth limit or expiration date. Because a black hole will never explode from absorbing too much mass, the only variable preventing one from consuming an entire galaxy is time. In 1971, Stephen Hawking proposed that some black holes never formed from collapsed stars at all. He theorized the existence of primordial black holes, entities forged from pure, intensely compressed energy in the first few nanoseconds of the Big Bang. Because they were born from pure energy, their density is difficult to visualize. A primordial black hole the exact size of a single microscopic proton would weigh as much as Mount Everest. A black hole the size of a coin would generate enough gravity to pull our moon into orbit. This extreme density leads many astronomers to believe these microscopic anomalies are the solution to the mystery of dark matter. Swarms of these invisible, microscopic black holes, rather than one giant central one, likely provide the missing gravitational influence needed to keep galaxies together. The Milky Way functions as a massive structural web, bound together by trillions of invisible, ancient anomalies scattered across the dark vacuum. When we look at standard black holes, the ones born from the death of regular stars, they naturally hit a ceiling. Because their parent stars are capped by the Eddington limit, the black holes left behind usually max out at around 150 solar masses. This presents a glaring mathematical paradox. If standard stellar black holes max out at 150 solar masses, there is no conventional path in physics that explains how we currently observe black holes weighing millions of solar masses. To bridge that massive gap, astronomers developed the Quasi-Star hypothesis, looking back to the extreme density of the early universe. In the early cosmos, gas was so dense that emerging stars absorbed thousands of solar masses at once. The gravity of these massive structures was so intense that before the full star could finish forming, its core immediately collapsed into a black hole, while the external layers remained completely intact. Trapped inside, the black hole acted as a parasite, rapidly expanding its mass by eating the host star from the inside out. The million solar mass titans we see today didn't grow through standard physics. They bypassed the universe's speed limits by gestating inside massive host stars, feeding in secret before breaking out. When you take objects that have bypassed normal physical limits and allow them to feed continuously for billions of years, you get the modern apex predators of the universe, ultramassive black holes. Consider galaxy OJ287. At its center sits a black hole with an event horizon so expansive that you could drop 3 of our entire solar systems inside of it side by side. But even that is dwarfed by TON 618. This titan weighs an incomprehensible 66 billion solar masses, radiating the brightness of 100 trillion stars. Its physical width breaks the human ability to conceptualize distance. If you entered TON 618's outer edge, traveling at the speed of light, it would take you a full week of continuous flight just to reach the center. At this scale, spatial measurements like miles or kilometers are useless. The only way we can comprehend their geometry is by measuring how long it takes the fastest thing in the universe to cross them. What we actually measure as the size of a black hole is just its event horizon, the shadow where light fails to escape. The physical object itself is the singularity at the core, an infinitely dense point. But the most terrifying detail about TON 618 is our vantage point. It sits 18 billion light-years away, meaning the gargantuan shadow we observe today is an ancient snapshot. The light reaching our telescopes left that black hole 10 billion years ago. Because black holes ignore all physical growth limits, their size is exclusively a function of time. They never stop feeding, and they never stop expanding. TON 618 provides a window into the potential of 13.8 billion years of unrestricted growth. In the deep, unseen present of the cosmos, the universe's true monsters have only just begun to grow.